Hey there! Let's talk about similarity, right triangles, and trigonometry. Starting off with the easiest one, similarity. Similarity kind of talks about involving dilations with two different shapes that look very similar with different values. So these two triangles, the smaller one would have a smaller value, but if you multiply it or add a certain value, you would get the bigger triangle. And they're all related some way by some kind of dilation, which means to increase or decrease by a factor. Let's look at the square. So it's centralized with the origin 0, 0, and the points are 1, 1, 1, negative 1, negative 1, negative 1, and negative 1, 1, just for example here. And what we're going to do is multiply this by a factor of 2 and see what happens here. If we multiply each point by 2, we would get the outer square right here. So this would be a dilation of the square by times 2. What happens if we times it by 3? Well, we'll just get the one even further outside. This would be times 3 because we're basically taking each point of the square and multiplying it by times 3. This is a dilation, and they're all similar because their values, when put in a proportion, they all work together, because if you just shrink it, they are the same triangle or square or whatever polygon you use. Now, how do we expand this to actual math? Well, let's see here. So let's say we have these two triangles. We know that they are separated by two parallel lines, and that if they are parallel, that means the opposite ulterior interior angles are congruent. So these two would be congruent, and then we would also have these two right angles, since these are the altitudes, also congruent. By that, we already know that we have two angles which are the same. We have 90 plus the congruent angle, so they have two angles in common. Well, we also know that by the sum of the triangles angles theorem, we know that the sum of all the angles is also, if you already know two angles, you know the third angle by subtracting by 180. So we could say 180 minus 90 minus congruent angle. So they both share three angles which are the same, because this angle by default they both share because they're the same angle. And thanks to that, we can say that we know these two triangles are similar, at least, maybe not congruent, but at least similar, because they share two angles the same, and technically three, which means that these are similar triangles thanks to the AAA theorem, or we could say the AA congruent theorem, because since they're already similar, we already know that they can be proven by two angles, and 3 is just an extra feature. Now let's talk about another topic here. Here's a great example of how we can use AA similarity properties to deal with types of triangles like this. Complex triangles, they're technically two triangles in one triangle, so we call them an overlapping triangle. And key things to note here is that side DE is parallel to side AC, and that's key here because now we know that there are some corresponding angles, which you'll remember from those theorems here. So angle D is congruent to angle A by the corresponding angle theorem, and another way to know that the AA theorem works here is that, as you can see, both triangles share angle B as a side, an angle, so we can say that they both share that angle, which means that they both have two angles in common, which also means they share a similarity of these two, the third angle. So we can say that these two triangles, triangle DBE, is congruent to triangle ABC, and that's because of the AA theorem. And because of that, we can find out the equivalence, the proportions of these two triangles. So we can say So a theorem we can say here is if side DE is parallel to side AC, which is what we're given in the beginning, then we can say that the line is parallel of one side of a triangle that divides the other two proportionally. And that means that this side right here, side BD over side DA, is equal to side BE and side EC. Now with right triangles, we can talk about similarity, and we can also talk about three main trigonometric functions here: sine, cosine, and tangent. Now, what each of them represents are different parts of functions, ratios of the triangle. Sine would be sine, that's how you would write it in a function, which would be hypotenuse, opposite, op over hypotenuse. Cosine would be cos, cos, equals adjacent, which would be the side right next to it that is not the hypotenuse, over the hypotenuse. The last one would be tangent, which we'll call tan, equals the adjacent, the opposite, my bad, over the adjacent. How would this look like? Well, for sine, it would be, let's say we're solving for this angle, we would say opposite over hypotenuse. And for cosine, it would be adjacent over hypotenuse, and tangent, it would be opposite over adjacent. We can have ratios for these different trigonometric proportions, and we can say that sine over cosine can be equal to tangent. Now why is that? Well, let's think about it. Sine is opposite over hypotenuse over cosine, which is adjacent over hypotenuse. If you cross multiply that, the result is opposite over adjacent, which is exactly tangent. And knowing these little things, we can solve great amounts of triangles. Now let's try this with a sample problem here. Let's say we want to find this angle, which I've marked with theta, a Greek letter that normally represents angles. We can use any of them since I've given you all these sides. So let's say we use tangent. Tangent would be tan theta equals opposite 5 over adjacent 12. If we enter that into our calculator, we should get about 22 degrees. 22, 23. And we can solve for, let's say, cosine, which would be adjacent over hypotenuse, which would be the same result. And for the last one, sine theta equals 5 over 13, and same result. They would all equal the same thing, but there's just different ways of getting the same result. Now let's talk about some formulas to apply to general triangles, not just right triangles. Let's say area equals 1/2 a times b times sine of c. So let's say this triangle here, let's say it's not a right angle. So let's just call 100, just for quality's sake. And we want to find the area. We know that if this would be CBA, sine of C. Now, let's just put some random values. Let's have 14, 25, 10. We need to find the area, and it's not a right triangle. So we have to make use of this formula here by plugging in A equals 1/2 A. The small a would be the side, which would be side A. So let's call that, well, we could say side A would be 14, and then we can say, after reconfiguring, we can say 14 Next would be side B, which would be 10. Again, look across. And the last one would be sine of C, which we know is 100 degrees. Your final result would be 68.9, let's call it, feet. Finally, the last thing we're going to cover are the law of sines and law of cosines, because of what they're using. And for this one, what we need to know is that it's very important to know that the sine A refers to the name of the angle. So let's say sine of A here would be this missing angle, and A would be the opposing side right here. So let's plug in this formula. So we would get sine of B, which is 130, over 75 equals sine of 10 equals 27. If we solve that out, and then we can actually plug in the missing angle, sine of A, equals, let's say A is 12, then we can plug it in to solve for A. And we would cross multiply for that. Now for law of cosines, we would get, for, let's say we're solving for A squared, which is the angle here, the side, and the angle would be A. So let's say the opposite side, let's call it 12, and 12 squared equals 75 squared plus 27 squared minus 2 times the side, 75, and 27 times cosine of 10. And we would get a result for those two. Thank you for watching. Hope this helped. And this has been Similarity, Right Triangles, and Trigonometry with SATFreePractice.com.